Hello and welcome to Algebra Workout. I'm Sally Ann Keyser and this is Alan Borthwick.
Hi. Algebra Workout is where we look at basic techniques in algebra and help you to use them.
I'll only ever need a pen and paper, albeit a sophisticated piece of paper, so we won't cover anything which you won't be asked to do as a typical student. I'll be solving lots of problems you'll be asked to do on your course, and I'll be concentrating on native wit and cunning, taking shortcuts where possible.
And it'll be my job to look at those problems in general, finding methods and rules that always work. I'll look in more detail and explain other ways of solving the problems. So, let's get started.
In this episode, the theme is rearranging formulas, things like expanding brackets, and we're going to have a look at a selection of quite different examples where you need to manipulate formulas in order to solve the problem.
Remember that the purpose of mastering these skills is so that they come naturally enough for you to concentrate on the interesting bits of mathematics without getting bogged down in technical details.
Expanding brackets is a technique you'll have to use a lot. In a minute, I'll be looking at a quadratic equation, x squared minus 12x plus 20 equals 0. Now I could use the general formula to solve this, but it does factorise.
And here's the generalised form for factorising the expression on the left-hand side. X plus a times x plus b, and we need to find the numbers a and b. So let's multiply this out in the usual way, taking every term in the first bracket and multiplying the second. X times x is x squared, then x times b will give xb. Then a times x, ax, and then finally, to finish the thing off, a times b giving the ab term. Now this xb plus ax will combine to give an expression a plus b in brackets times x. And let's compare this whole expression with the original left-hand side. X squared minus 12x plus 20. Now the a plus b is equal to the negative 12 and the ab is equal to the 20, and we get two equations. A plus b is negative 12 and ab is 20. And we need to solve these.
Another way of saying that is that whatever the two numbers a and b in the brackets are, their sum must be equal to the x term. In this case, that's minus 12. And their product must be equal to the final term, in this case 20. So let's think about what those numbers a and b might be here. Since there are fewer pairs of numbers which multiply together to make 20 than there are numbers which add together to make minus 12, I'll consider those pairs first. Then I'll be able to just look at which two combine to make minus 12. OK, so what numbers multiply together to make 20? This is just the same as asking what are the factors of 20? Well, there's 1 times 20, then 2 times 10, and then 4 times 5. And as also two negative numbers make a plus, then I also have minus 1 times minus 20, minus 2 times minus 10, and minus 4 times minus 5. So my question is, which of these pairs adds together to make minus 12? Well, if you try each pair in turn, you'll find it's minus 2 and minus 10. It doesn't matter which is A and which is B, and I can just plug these numbers straight into my brackets. So I have x minus 2 and x minus 10, and that's all equal to the 0. So I can solve the quadratic completely because I can see immediately that x is equal to 2 or x is equal to 10.
But what if I had to factorise an expression where the x squared term had a coefficient that wasn't 1? What about something like 6x squared minus 11x minus 10? Well, it's not actually much trickier. Let's just think about it a bit. We need two brackets, and the first term in each bracket must multiply to give the 6x squared. So we could have, in the two brackets, 2x and 3x. Or there again, we could have an x and a 6x. And it doesn't matter which way around the brackets are, as long as the two first terms multiply to give the 6x squared. Now let's think about the constant negative 10, because the two latter terms must multiply to give negative 10. And there my magic board's given some suggestions. Negative 1 and 10, 1 and negative 10, negative 2 and 5, or 2 and negative 5. And at that stage, it's just a question of trial and error, trying all the possibilities. Let's see what the magic board does. And there we have it. 6x squared minus 11x minus 10 is equal to 2x minus 5 times 3x plus 2. The middle term being the minus 15x plus the 4x, giving minus 11x. So as I said, it's really just a question of trying all the possibilities. Sometimes you might be lucky and get the answer the first time you try, or you may have to have several goes. The more you practice, the more you'll get a feel for what the answers are. And although you can always use the general formula for solving quadratics, it's sometimes much quicker and easier to factorise.
Now let's have a look at a completely different kind of example of rearranging formulas. 2 plus root 3 over 1 minus root 3 is equal to minus 5 over 2 minus 3 over 2 root 3. What is it that I have to do to the left-hand side in order to get this expression? Well, a good thing to do might be to get rid of that 1 minus root 3 in the denominator.
Now, in this kind of example, it's useful to use a formula which we call the difference of two squares, and you'll see why in a minute. Let's look at this factorised expression and let's expand it. A times A is going to give us the first term of the expansion, A squared. Then AB, second term, minus BA, third term, and finally the minus B squared. These two middle terms will now cancel to give A squared minus B squared. So we get the expression A minus B times A plus B is equal to A squared minus B squared. And this is where the name difference of two squares comes in. Now let's go back to Sally Ann's expression. What I'd like to do now is multiply top and bottom by 1 plus root 3. And the reason for that is as follows. That 1 minus root 3 times 1 plus root 3 is a difference of squares. It comes to A squared minus B squared. And the magic board shows you that that gives minus 2 in the denominator. And the root 3 that was there has now totally disappeared.
Well, that looks very useful for my problem. I can multiply the denominator, the bottom, by 1 plus root 3, which will get rid of the root 3. But then I also have to do the same to the top, to the numerator, to balance things out. So, if I multiply the top, 2 plus root 3, by 1 plus root 3, I also have to multiply the bottom, 1 minus root 3, by 1 plus root 3. And multiplying out these top brackets, that gives me 2 times 1 is 2, plus 2 times root 3 is 2 root 3, plus root 3 times 1 is root 3, plus root 3 times root 3 is 3. And on the bottom, as Alan showed us using the difference of two squares, I have 1 squared minus root 3 squared. So on the top, 2 plus 3 is 5, plus 2 root 3 and root 3 is 3 root 3. And that's all over 1 squared minus root 3 squared, 1 minus 3 is minus 2. And breaking this up into two fractions, that gives me 5 over 2, and that's a minus 3 over 2 root 3, which I can see is my original right-hand side.
OK, let's look at just one more problem before we finish. It involves expanding brackets, of course, but it also involves some extra algebraic tricks.
The equation is 3 times 2 to the n plus 5 to the n all squared is equal to 9 times 4 to the n plus 6 times 10 to the n plus 25 to the n. Again, what I'm really interested in is how I can manipulate the left-hand side to get the right-hand side.
Well, this expression, which is the left-hand side of the equation, might look a bit complicated, but basically it's of the form a plus b all squared, where a is 3 times 2 to the n and b is 5 to the n. So we want to know how to expand a plus b all squared. And the first thing we have to do is write it as the usual product of two brackets and then get multiplying. A times a gives a squared, a times b gives the AB term, then we have a BA and a B squared term. But you'll notice the two middle terms are the same, so they can combine to give 2AB. And our expression becomes A plus B times A plus B is A squared plus 2AB plus B squared. Now what if we had a minus b times a minus b? Well, in that case, the expression is basically the same with a negative sign at the middle term. A squared minus 2ab plus b squared. And these are really important expressions to attempt to remember.
Right, I'll use that now to expand the left-hand side of my equation. So 3 times 2 to the n is a, and 5 to the n is b. So if I think of that as a squared plus 2ab plus b squared, then I'll get a squared, 3 times 2 to the n, all squared, plus 2ab, that's 2, a, 3 times 2 to the n, b, 5 to the n, plus b squared, which is our 5 to the n, all squared.
Now I just want to interject very quickly here and emphasise a rule which I know that Sally Ann is going to be using. It's quite simple really. A b to the power p is a to the p times b to the p. Or a to the p times b to the p is ab, the product, all to the power p. This can be clarified by using some numbers. Say we have 2 to the n times 2 to the n, then that will be 2 times 2, 4 to the n. Or another example, say we have 2 to the n times 5 to the n, that would be 2 times 5, 10, all to the power n. Simple as that.
Thanks, Alan. Now I can use that rule as well. So looking at this first term, squaring each term gives me 3 squared is 9 times 2 to the n squared is 2 to the n times 2 to the n, which I now know is 4 to the n, plus 2 times 3 times 2 to the n times 5 to the n. 2 times 3 is 6 times 2 to the n times 5 to the n, I now know is 10 to the n, plus 5 to the n all squared is 5 to the n times 5 to the n. That's 25 to the n, which is exactly what I had on my original right-hand side. So careful rearrangement, taking care with powers along the way, can be very useful in breaking down complicated expressions.
Now I hope you followed what we've done. If you didn't, you can always rewind the tape and have a look through it again. Good luck with tackling other examples.